All right, everybody, let's talk earthquakes. We're going to look at the characteristics of earthquakes, the causes. We're going to discuss seismic waves, and this is part of our seismology portion of earthquakes. Later, we'll look at magnitude and intensity, which is the strength of the earthquake, and then also the location and the damage. You can see pictured here the Anchorage, Alaska earthquake of 2018 in November. An example of what can happen when a 7.0 magnitude earthquake strikes. Alaska is no stranger to strong earthquakes. They typically have lots of earthquakes that are very damaging. All right, so here we go with the characteristics and causes. First off, the definition of an earthquake essentially is movements of the ground that are caused by sudden release of energy when rocks along a fault move. Standard definition. When we're talking earthquakes, we're talking energy. Very much like wind energy passes through water creating waves, seismic energy is built up elastic energy in rocks that's released in the rocks and passes through the rocks in waves. And of course, that wave behavior in rocks causes them to rumble and move. Earthquakes are typically and most commonly generated from slippage along fault lines. Fractures in which cause movement are the definition of faults. And so this is the most common cause of earthquakes. Pictured in the lower left here is the San Andreas Fault in California, a very active fault in our continental United States. And pictured on the right is a parking garage that is destroyed. This is from the earthquake in 1973 in the San Fernando Valley in California. This one was an earthquake that occurred in and around the Los Angeles area, so a pretty highly populated area. Characteristics. First off, the slippage along a fault is called the focus. A fault plane can be hundreds or even thousands of kilometers long and tens to hundreds of kilometers deep or even more. And so the fault surface is very big. And really, when an earthquake occurs, it's because one section of that fault surface slips. Typically, the entire fault surface is locked and loaded, and pressure in the Earth's crust is building up. And when that pressure is released, this is when you have earthquakes. Now, you're probably familiar with the term epicenter. That is the term that is directly above the focus on the surface of the Earth. So the point directly above the focus on the surface, epicenter. Our prime example for faults is the San Andreas Fault here in the United States, along the coast of California, all the way from the northern part of California down through San Francisco and Parkfield. Further south, north of Los Angeles, is the San Andreas Fault. It's creeping all the time. You'll notice the motion here. You see the arrows pointing on this. One arrow going up to the northwest, the other to the southeast. A quick review question for you. What type of stress is that? The stress that moves in opposite directions. Shear. Yeah, shear stress. And then what is the type of plate boundary then associated with this, do you think? Transform, right? Transform. And the type of fault then, strike slip, strike slip. The cause of earthquakes is primarily what we call the elastic rebound theory. And the elastic rebound theory is essentially a buildup of stress in rocks that's suddenly released. Okay, as the stress in rocks build up, rocks actually behave elastically. We don't think of them as elastic materials. You don't think of rock like a rubber band, but when subjected to enough stress, rocks actually behave elastically. And so they'll bend, and gather more and more and more stress. And eventually, when they slip, they snap back into place and they release that stress. This is the elastic rebound theory. I've got a picture of what that might look like on the left here with the fault line having stress build up. And then the third picture down shows the release or the slippage along the fault, which releases all that built up energy. And then once it's released, it goes back to a stable form for a little while. Taking a piece of stick, like a stick, and bending, and then snapping it. This is also an analogy here pictured, where the original position builds up energy. The rupture causes the energy to be released, and then you're there. So this is the elastic rebound theory. We're going to skip over that. The energy then is released in what we call seismic waves. Okay, seismic waves are energy moving through the Earth's crust that behaves in wave form. Seismic waves are the vibrations that are caused by that cause earthquakes. And there are two waveforms that propagate through the Earth. Kind of a push-pull compression wave called P waves, and a shear version of those waves called S waves. Now these waves, they pass all the way through the Earth. The picture here shows the epicenter of an earthquake and the focus probably just below, but you can see these curved arrows showing how the waves move through the Earth. They actually take a curving path because of the changing density and pressure as you get deeper in the Earth. But these waves actually curve themselves through the Earth. And so when an earthquake occurs, even here far up north, it can be felt almost all over the entire Earth. We'll also note that when these so-called body waves, which are the P and the S waves, when they interact with the surface, they generate what we call surface waves. And those are named after the scientists who recognize the different waveforms of those, Love waves and Rayleigh waves. Now, these only travel over the surface, and they are generated by those P and S waves. But Love and Rayleigh waves are the most destructive of the waves. So we're going to dive into the nitty-gritty here about these seismic waves, and I'll go through each as we pass through these slides. First off, the P waves. Now, P waves are called P waves because they are just that, primary. They are the first to arrive. Primary waves are the fastest of the waves, which is why they're the first to arrive at a seismometer, a device that records these seismic waves. So P is for primary. They're fast because of their compression or compressive motion, this back and forth sort of push-pull motion as they pass through the Earth. And this motion, this compressive motion, is actually pretty efficient. It can pass through solid and liquid. Of course, it moves faster through the solid. It slows way down in liquid, but it actually still can move through liquid. This compression or back and forth motion is shown in the picture here on the left. You can see that the material is stretched out in some locations and scrunched together in other locations. When the wave of energy passes through the rock, it stretches or scrunches the rock, and then when it moves out of the rock returns to its original undisturbed form. And so this shows, of course, that rock is elastic, that it can be pushed and pulled and moved, and the energy released in seismic waves does this. I would liken the movement of a P wave to that of an earthworm. Kind of a stretch and scrunch sort of motion. Stretch and scrunch. This is a compressive motion. The second type of wave in an earthquake is an S wave. S waves are called S for secondary because they are the second to arrive at a seismometer. They're the second fastest wave. They're a little slower than P waves, and they can't move through liquid. This motion is not as efficient. You can see the picture on the right shows how the shear motion of the wave moves and kind of creates a wavy motion through the rock that would be likened to like maybe the worm. So if a P wave is like an earthworm, then S wave is like the 80s dance move the worm in a shear sort of motion. The next type of wave here, surface waves. Surface waves are your waves that are generated from the P and S waves from below. So when the body waves come and disturb the surface, they basically create two motions in the earth along the surface. The first motion is a backwards rolling motion that you see pictured in the upper left. This is called a Rayleigh wave. And the one in the bottom left shows a love wave, which is a side-to-side sort of motion created from the P and the S wave activity at the surface, propagating from the epicenter. Now, surface waves are the slowest moving waves, but they're the strongest and most destructive. They cause the surface to rise and fall and move backwards and forwards. And they are actually most destructive in loose earth. As it turns out, earthquake waves that pass through hard, solid bedrock ring through it like a bell and don't cause a lot of shaking on the surface. Earthquake waves that pass through softer sediment cause a lot of shaking and therefore a lot of damage. If I had to pick one that's the most destructive, it'd probably be Rayleigh waves when it comes to destructive power as things move through the surface. We'll talk about this more when we talk about earthquake damage, but it is of note that earthquakes don't kill people, buildings kill people. So when you're looking at earthquake damage, it's important to recognize what sorts of earthquake waves would have the biggest effect or the most damaging effect on the buildings. And oftentimes it's the Rayleigh wave. But love waves and actually P and S waves are pretty destructive also. As I mentioned before, seismic waves can pass through the entire Earth, and therefore earthquakes that occur can be recorded all over the Earth. In this picture on the right, I have an earthquake occurring in Alaska. But this earthquake can be felt everywhere in the northern hemisphere. You can see in the picture, there's just only a small portion here, a little shadow area. It's called the P wave shadow zone, where earthquake waves cannot be felt. Remember that as earthquake body waves pass through the earth, these P and S waves, they have a curving path because of the changing densities and rock as they move through. When they get to a certain point, they hit that outer core, and all the S waves, because of that shear motion, are absorbed. And so S waves kind of stop after that. But the P waves, they travel through and they change speed and direction as they pass in and out of the outer core there. And they can be actually felt on the opposite side of the Earth. But there is a zone here from like 103 degrees to about 143 degrees in all directions around away from the earthquake that do not feel the earthquake itself. What's more is that much of what we know about Earth's interior structure comes from seismic waves. Because we can see the speed and direction changing of these seismic waves, we can determine what the Earth's interior layers look like. Here's another look at these shadow zones, showing the P wave in purple here, curving through the Earth in all directions, able to be felt all the way around the Earth near the earthquake, and then actually even behind the Earth in some locations because of that change of speed and direction. There are some P wave shadow zones, though. You can see this little stick figure here, and then over here, this is where the shadow zones would be for the P waves. And then the S waves are shown in pink, and those propagate all the way around the Earth from the earthquake, but get absorbed by the outer core. So really, you can only feel the S waves in a certain zone away from the earthquake. As you get further away on the opposite side of the Earth, you can't feel those S waves. That would be the entire back side of the Earth would be the S wave shadow zone. Pause for a moment to have you write this down or diagram it on your notes. They measure these earthquake waves with what we call a seismometer. It's sometimes called a seismograph. This is a device that measures and records all the seismic waves. Traditionally, it's been a kind of a system where a pen is or a marking device is suspended from a series of weights and springs in order to stay stationary. So if you look at the pen in the lower left here or the pen in the middle bottom, you would see that the suspended mass there stays in one place as the Earth moves, but the rotating drum of paper continues to move, and it will move with the Earth. So it'll move up and down or side to side with the motion of the Earth, and therefore it produces a series of squiggles, and those squiggles are a measure of the strength of the earthquake. So seismometers measure the strength of the earthquake's wave shaking. Now, back in the ancient days, before they had these seismometers, they came up with some pretty creative ways in order to measure the earthquake's strength. Pictured here in the middle left is an ancient seismometer from China. Now, mid-continent China has a lot of earthquakes, and we'll talk about why that is in future lectures. But you can see here that there is a big jug of water, and it's filled up just to the brim so that if there's any shaking, water will come out of these little dragons and spill into the mouths of these frogs. And these frogs are attached to a container underneath. So however much water is captured from the shaking of the earthquake, that's how strong the earthquake was. So this is a creative old way to measure the strength of earthquakes. This would be an ancient seismometer. But a seismometer is the device that measures the strength of the earthquake's shaking. Okay. Modern seismometers will produce a seismogram. And a seismogram is the paper record taken by the seismograph or seismometer. And we can measure magnitude or strength of the earthquake from this. Essentially, the size of the squiggles equals the magnitude of the earthquake. And now there are many ways to calculate this from the magnitude or from the seismogram, but you can see pictured here, a basic seismogram will give you the P wave arrival and time of the P wave arrival, and the S wave arrival time, again, secondary to the primary wave. And then the surface waves after that, typically coming at a later time because they're the slowest of the waves, but most damaging, so you can see the big surface wave squiggles there. Again, the strength of the earthquake really is measuring the energy released by the earthquake. And that energy ultimately comes from the buildup of elastic strain in the rocks through the elastic rebound theory. So those are the characteristics and causes of earthquakes, and a little bit about the seismic waves, the study of which is called seismology.